What is an RTN and why every telecom engineer should understand it? There is a moment in every new telecom engineer's career when they realize that getting a base station on air is only half the battle. The radio unit can be perfectly configured. The BBU can be running without a single alarm. The antennas can be aligned to the centimeter. But if the traffic that site generates has nowhere to go, if there is no path carrying data from the base station back to the core network, the site is an island. Loud, capable, and completely cut off. The equipment that solves that problem is the RTN, the radio transmission node. And understanding it is not optional for any engineer who wants to work confidently on modern telecom infrastructure. What the RTN is? The RTN is a microwave transmission equipment that carries traffic between a base station and the wider network. It is the backhaul link, the connection that takes everything the base station processes and moves it onward to the operator's core network where calls are routed, data sessions are managed, and the wider internet is accessed. Without a backhaul link, a base station cannot serve users in any meaningful way. The radio side of the site handles the connection between the tower and nearby mobile devices. The backhaul side handles the connection between the tower and everything else. The RTN is what makes the backhaul side work when microwave transmission is the chosen medium. In practice, the RTN is a compact but sophisticated piece of hardware. It manages the modulation of outgoing traffic into microwave signals, the demodulation of incoming microwave signals back into data, the management of transmission capacity and quality, and the interface between the base station equipment and the microwave link. It does all of this continuously, in real time, while the site is live and serving users. The connection between the RTN and the BBU. The RTN and the BBU sit together in the equipment room or cabinet at the base of the tower. They are the two core pieces of indoor equipment at any microwave backhauled base station site, and the connection between them is the first link in the chain that carries traffic from the air interface all the way to the core network. The BBU connects to the RTN via an Ethernet cable. On the BBU side, this connection uses one of the unit's Ethernet service ports. Depending on the vendor and the BBU model, these ports may be standard GE ports, gigabit Ethernet, or higher capacity 10 GE ports for sites with greater traffic demands. These ports are typically located on the baseband processing boards inside the BBU, and their configuration determines how much traffic the BBU can hand off to the transmission network. On the RTN side, the connection arrives at one of the unit's tributary ports. These are the ports designed to receive traffic from the base station equipment and feed it into the RTN's internal processing system. The RTN's tributary ports also support Ethernet interfaces, creating a clean and standardized connection point between the baseband and transmission domains. This Ethernet link between the BBU and the RTN is the handover point between two distinct worlds. On the BBU side, traffic is organized according to mobile network protocols, LTE frames, 5G NR packets, voice sessions. On the RTN side, that traffic is prepared for microwave transmission, aggregated, prioritized, and formatted for the journey across the air to the next node in the network. The Ethernet cable between them is simple in appearance but critical in function. Some BBU models also carry SFP ports, small form factor pluggable interfaces, that can be used for transmission connectivity when the site uses fiber rather than microwave. But in the microwave backhaul scenario, it is the Ethernet port that carries the traffic to the RTN. The connection between the RTN and the ODU. Inside the equipment room, the RTN handles the baseband and lower frequency processing of the microwave link. But the actual microwave signal, the radio frequency energy that travels through the air to the next tower, is generated and received by a separate outdoor unit called the ODU. The outdoor unit. The ODU sits outside, mounted on the tower or rooftop, pointed precisely at its counterpart ODU on the distant tower. It is the unit that actually transmits and receives microwave signals, converting between the intermediate frequency signals it receives from the RTN and the high-frequency microwave signals it sends into the air. The connection between the RTN and the ODU runs through an IF cable, an intermediate frequency cable. This is a coaxial cable that carries signals at an intermediate frequency range, typically between 70 MHz and 140 MHz or in the L-band range around 1 GHz depending on the system. The IF cable runs from the RTN's ODU port, exits the equipment room through a weatherproofed cable entry point, travels up the tower or across the rooftop, and connects to the ODU at its mounting position. The IF cable serves two purposes simultaneously. It carries the outgoing IF signal from the RTN up to the ODU for transmission, and it carries the incoming IF signal from the ODU down to the RTN for processing. It also carries the DC power supply from the RTN to the ODU, meaning the ODU does not need its own separate power feed. The RTN powers the ODU through the same coaxial cable that carries the signals, a practical design that simplifies installation and reduces the cabling required at the tower head. The length and quality of the IF cable matters. Signal loss in the cable increases with length, and exceeding the maximum recommended cable run for a given system can degrade the link performance. Engineers must account for cable length during site planning and select appropriate cable specifications to ensure the signal integrity between the RTN and ODU is maintained. Where modulation and demodulation occur. Understanding where modulation and demodulation happen in the RTN-ODU system is important for engineers troubleshooting transmission faults or optimizing link performance. Modulation, the process of encoding the digital traffic data onto a carrier signal for transmission, occurs inside the RTN. The RTN takes the digital data arriving from the BBU, processes it through its modem, and modulates it onto an intermediate frequency carrier. This modulated IF signal is what travels up the IF cable to the ODU. The ODU receives the IF signal from the RTN and performs a frequency conversion, upconverting the intermediate frequency signal to the actual microwave transmission frequency. For a link operating at 18 GHz, for example, the ODU takes the IF signal at perhaps 140 MHz and shifts it up to the 18 GHz band for transmission through the air. This upconversion is done using a local oscillator and mixer circuit inside the ODU. The resulting microwave signal is then amplified and transmitted through the ODU's waveguide interface into the dish or horn antenna pointed at the far end of the link. On the receive side, the process reverses. The ODU's antenna captures the incoming microwave signal from the distant tower. The ODU downconverts that microwave signal from the high transmission frequency back down to the intermediate frequency range and sends it down the IF cable to the RTN. Inside the RTN, the modem demodulates the IF signal, extracting the digital data from the carrier and delivering it as Ethernet traffic to the BBU. So in summary, modulation and demodulation are RTN functions. Frequency upconversion and downconversion are ODU functions. The IF cable is the interface between the two domains. This division of responsibility is important to keep in mind when faults occur. A modulation or demodulation problem points to the RTN. A frequency conversion or antenna alignment problem points to the ODU. The brief function of the ODU in transceiving microwave signals. The ODU's job is focused and specific. It is not a complex multifunction device. It exists to do one thing well: convert between the intermediate frequency domain of the indoor equipment and the microwave frequency domain of the transmission link. On transmit, it upconverts the IF signal to microwave frequency, amplifies the signal to the required power level for the link distance, and radiates it through the antenna toward the far-end ODU. On receive, it captures the incoming microwave signal, filters it, amplifies it with a low-noise amplifier to recover the signal cleanly without adding significant noise, and downconverts it to IF for delivery to the RTN. The ODU is built to survive outdoor conditions, temperature extremes, rain, wind, humidity, and UV exposure. Its housing is weatherproofed and its interfaces are sealed. The waveguide connection between the ODU and its antenna is a precision mechanical interface that must be correctly assembled and weatherproofed during installation to prevent moisture ingress, which can degrade or destroy the connection over time. Microwave frequencies used by ODUs in mobile backhaul typically range from 6 GHz up to 86 GHz depending on the link distance and capacity requirements. Lower frequencies travel further and are less affected by rain fade but carry less capacity. Higher frequencies carry more capacity but are more sensitive to atmospheric conditions and limited to shorter link distances. The RTN and ODU are matched to the same frequency band, and engineers must verify this compatibility during equipment selection and installation. When optical fiber is used instead of microwave. Not every base station uses microwave backhaul. In many urban environments, and increasingly in suburban areas as fiber infrastructure expands, base stations connect to the core network through optical fiber rather than microwave links. This raises a question that engineers new to transmission often ask. If the site uses fiber, is the RTN still relevant? The answer depends on the specific equipment configuration, but in many fiber-based deployments the RTN is not required. When optical fiber is the transmission medium, the BBU connects directly to the fiber network through its SFP ports. An SFP optical transceiver module is inserted into the BBU's SFP port, A fiber patch cable connects it to the fiber termination point in the equipment room, and from there the traffic travels over the fiber network to the core. The RTN and ODU are not part of this path at all. However, this does not mean the RTN disappears from the picture entirely in mixed environments. Some sites use a combination of fiber and microwave, perhaps fiber as the primary backhaul with microwave as a backup link that activates if the fiber fails. In these configurations, the RTN remains installed and configured as a standby path, ready to carry traffic if the primary fiber link goes down. There are also transition scenarios where an existing microwave backhauled site is being upgraded to fiber. During the transition period, both the RTN microwave link and the new fiber connection may be active simultaneously, with traffic migrated from one to the other in a controlled process. The RTN continues to play a role until the migration is complete and the fiber link is confirmed stable. Equipment between the BBU and core in a fiber transmission scenario. When optical fiber is used for transmission, the equipment chain between the BBU and the core network looks different from the microwave scenario but follows its own clear structure. From the BBU's SFP port, fiber connects to an optical distribution frame, the ODF, in the equipment room. The ODF is a termination and patching point for fiber cables, allowing the site's internal fiber connections to be neatly managed and connected to the external fiber infrastructure. From the ODF, the fiber runs into the external fiber network. Depending on the network architecture, the next node in the chain may be an aggregation switch, a device that combines traffic from multiple base stations onto a higher capacity fiber link for the journey to the core. This aggregation switch may be located at a nearby hub site or roadside cabinet. From the aggregation layer, traffic travels over the operator's transport network, typically a high-capacity dense wavelength division multiplexing system, or DWDM, which carries multiple separate data streams on different wavelengths of light over a single fiber, toward the core network. At the core network boundary, the traffic arrives at the operator's mobile gateway equipment, where it is processed, routed, and connected to the wider internet or telephony infrastructure. The key point is that in a fiber scenario, the transmission function is handled by the fiber network's own equipment, optical switches, aggregation nodes, and DWDM systems, rather than by the RTN. The BBU interfaces directly with that infrastructure through its SFP port, and the RTN's role is replaced by the fiber network's own devices. Why every engineer should understand the RTN. The RTN sits at the intersection of the radio domain and the transmission domain, the two worlds that a complete base station engineer must be able to navigate. Engineers who only understand the radio side can commission a perfect BBU and RRU configuration, but cannot diagnose a backhaul fault. Engineers who only understand transmission cannot trace a problem from the core back to the air interface. Now, if you're still watching, congrats. Most people don't reach here. Leave a comment below, let us know what you think about the RTN. To continue, the RTN is the device that bridges those two worlds. Understanding how it connects to the BBU, how it drives the ODU through the IF cable, where modulation and demodulation happen, and how its role changes when fiber replaces microwave. All of that knowledge makes an engineer more complete, more capable, and more valuable on any site they work on. In a field where the difference between a stable network and a failed site often comes down to one engineer's ability to understand the full chain from antenna to core, the RTN is not a detail. It is a foundation. Thanks for watching and keep looking.